Okay, today is day 25. I think everybody, myself included, will be glad that we have arrived at this day because we not completely forget about the definition of derivative, but we do get some shortcuts today, an exponent rule or a power rule when it's legal. It's actually legal to use quite a bit. Some derivative, if we have time, derivative of exponential functions, derivative of a sum, the derivative of a difference, and the derivative of a constant times a function. So it's a good day in that regard. What we don't get to today in Chapter 3, Section 1, we will finish tomorrow. So we actually have 2 days to do it. So we can get a look at plenty of examples also. Here are some things that we have actually come across, but we may need to spend just a moment or two in validation. Derivative of a constant function. Now, if you just think about it for a second, a constant function, if you graph it, what does it look like? Okay, straight line. What kind of line? Give me a little more information. Horizontal line. So all constant functions are horizontal lines. Now, if we talk about the derivative being the slope of the tangent line, how do you get to be tangent to a horizontal line? Well, the only way you can be tangent to it is to coincide with it. And what's the slope of a horizontal line at any place? Zero. So the derivative of a constant is zero. So hopefully visually that makes sense to you, that we've got these horizontal lines. You can't really be tangent to a horizontal line without, in essence, coinciding with it, and the slope of a horizontal line is zero. So that's very helpful. And believe it or not, as simple as this concept is, it gets missed from time to time. And I think you overlook it. I think you just say, well, there's a 5, the derivative of 5 is 5. Well, no, it's not. The derivative of y equals 5 is 0. Derivative of every constant is 0. The derivative of x with respect to x, in fact, that almost looks like 1, doesn't it? If you write it the right way, or a different way, doesn't that look like 1? Dx over dx. So that's a good little visual there. But the line y equals x, can you visualize that line in the plane? Okay, what's the slope of that line? 1. So what's the slope of any line that's tangent to it? Well, you can't be tangent to it without coinciding with it. So the slope of every tangent line would be 1, the same as the slope of the line itself. So hopefully visually those two things make sense. And we've done some others also. We have done some other derivatives through our process of looking at the definition of derivative. We've done the derivative of x squared, the long way, using the definition. If you check back through your notes, you will find that the derivative of x squared was 2x. And we found that using the definition of derivative. We've also done the derivative of x cubed. Actually, I think we did the function x cubed minus x. But the x cubed portion of that, the derivative of x cubed was 3x squared. Now, we're kind of developing a little bit of a pattern. Let's see if the same pattern that you think you're seeing or that you already know from a previous math course, let's see if, in fact, we can take the derivative of x to the 4th the long way. And now and then we're going to have to go back to the definition, but most of the time from this point forward we'll be using shortcuts. So the function is x to the 4th, and we want the derivative of that function with respect to x. And Umair, since you're the shortcut man of this class, what is the answer going to be, hopefully, if this pattern works out? 4x cubed, right? So it should be, and there's another reason why I want to do the long method here. Just because it's kind of sad to not do this anymore. That's not true. There's a reason why I want us to look at the long method because of the binomial x plus h to the fourth. I want to talk about how to take a binomial and raise it to the fourth or the seventh or the 11th or the 20th without having to work too hard at it.
Can you use the binomial too?
Yes. But in its truest sense, I'm not sure how many of you know that. The n times n minus 1 over 2 factorial, n times n minus 1 times n minus 2 over 3 factorial. So, okay, so I just want to make sure, but that's why I want us to look at this. All right, so there's the, by definition of derivative, we're going to take the derivative of the function y equals x to the fourth. So x plus h to the fourth minus x to the fourth all over h as h approaches 0. Here's the reason why I wanted us to look at this. Let me take this paper away and let's spend a few moments with x plus h to the fourth or some other higher power, and then we'll come back to this. How does that expansion go? Okay, the coefficients are 1, 4, 6, 4, 1. Now you can get them from Pascal's triangle. Pascal's triangle gives you the coefficients of a binomial to higher powers. Here we are, 1, 4, 6, 4, 1. Have you seen this before? What am I doing to get these numbers each time? Adding the 2 above, right? So I'm adding 3 and 1 to get 4, 3 and 3 to get 6, 3 and 1 to get 4. And these would be the coefficients of some x plus h or a plus b, some binomial to some integer power, positive integer power. So this would be the coefficients of, let's say, x plus h to the 0, right? Because x plus h to the 0 would just be 1. These would be the coefficients of x plus h to the 1, right? 1x plus 1h. And then as you continue, this ought to look familiar. Those would be the coefficients of x plus h squared. 1x squared plus 2xh plus 1h squared, right? And then you could use that. Now I think there's a better way. There's a little more concise way we could develop this, but let's, since that's our starting point, the first term ought to be 1 x to the fourth, right? According to this line right here. These would be the coefficients of a binomial expanded to the fourth power. Then we should have 4. Power of x would be cubed. Power of h would be to the first. 6 x squared h squared, right? The x's are descending, the h's are ascending, right? Plus 4x h cubed, and then 1h to the fourth. So look at the powers of x as we go through the expansion. X to the fourth, x to the third, x squared, x, and then x to the 0, which is a constant, right? Is that visible? Look at the powers of h as you go through. There's an h to the 0. It's probably not real visible there, but there is an h to the 0, right? Then there's an h to the 1, h to the 2, h to the 3, and h to the 4. And then those coefficients, which we found this way, then there's another way to get these coefficients. And that's what I want us to look at. Now, if we know that if you multiplied x plus h times itself 4 times, the first term, x times x times x times x, is going to generate the first term of the expansion, right? X to the fourth. So there's not a mystery to that. Now, once we get that, we can take this exponent and multiply it by this coefficient, which is 1. Divide it by the number of this term, and that generates the next coefficient. Now let's see if that pattern works. So the next coefficient should be 4. We should be able to take this exponent times this coefficient, divide it by the number of this term, which is 2, and that should generate the next coefficient. Is that correct? How many of you have used this pattern before? This pattern that I'm talking about right now? Okay, that's why I wanted us to look at this in class. It's kind of a clean little pattern, actually, and it's easy to write down in terms of letters and numbers what we're actually doing. So that'd be 12, that'd be 6, x squared, h squared. Take this 2 times this 6, divide it by 3, because this is the third coefficient. That ought to generate the next one. It is, but it's disguised right now. This is a different way of actually beginning it. So that'd be 12 divided by 4, x h cubed. Take that 1 times that 4, divide it by 4, and that ought to generate the last coefficient, which is 1 h to the 4th. Seems to work, doesn't it? Yes, Travis.
Could you explain again where the numbers come from in like the 4, the 1, and the
Okay.
1?
This 4 is from our original first term exponent. Okay, and if you're going to raise something to the 4th, so if you were writing this out, x plus h times itself 4 times, then the first term would be x times itself 4 times. So there's the first term, and it'll always be x to, or the first term of the binomial to that power. So once you get this, take 4 times the 1 that's already here, divide it by 1, since this is the first term, and we're trying to generate the coefficient of the second term, and then follow that pattern. 3 times 4 divided by 2, this is the second term, trying to generate the third coefficient. 2 times 6 divided by 3, this is the third term, trying to generate the fourth coefficient, and so on. Is that okay? Does that answer it? Any other questions on this one before we go ahead? Everybody, is the pattern somewhat believable? Is it believable enough to take x plus h, I don't know, to the 7th? Let's just make up another number here. Let's see if we can run that one out. The first term is no mystery, x to the 7th. What's the next term? 7, right? We take 7 times 1 divided by 1. Next term, next coefficient.
21.
21, right? 6 times 7 divided by 2. 5 times 21 divided by 3, right? What's that?
115 divided by 3.
105 divided by 3, 35? Is
Never mind.
that right? Next coefficient, 4 times 35 divided by 1, 2, 3, 4. 35 again. It's working, isn't it? You can check it out. Actually, if you want to, if you have some spare time this afternoon, since it's raining, so nasty and cold, just sit down and multiply x plus h by itself. Don't really do that. Don't ever do that. The rest of your life, don't do something like that. X plus h to the 7th, but this is a nice, clean, quick way of expanding something. Now, let's just finish this one. What would this be? X to the 3rd, h to the 4th, 3 times 35 divided by 5, which is 21, x squared, h to the 5th, 2 times 21 divided by 6, is that right? 7, x, h to the 6th, and the last term we already know is going to be 1, h to the 7th. So it doesn't matter what it is, the 7th power, 11th power, 20th power, that pattern will get you the correct expansion. Now, what I want us to come back to, let's finish this little problem, x plus h to the 4th, and let's come back to x plus h to any positive integer power, n. Okay, so we'll come back to this problem in a moment, but at least we've got the pattern established. Okay, let's see. Here we are. X plus h to the fourth, x to the fourth, plus 4x cubed h, plus 6x squared h squared, plus 4x h cubed, plus h to the fourth. Everybody all right with that? We did that 2 different ways, and that's what we got. So we've seen this happen. Not much of it is taken care of here, but x to the fourth minus itself. Everything in the left in the numerator has an h, is that correct? Keep that in mind. That's very important to the first shortcut, that every term that remains in the binomial expansion has at least h to the first. In fact, most of them have a lot more than h to the first. And we've seen this happen before. What's the advantage of factoring out the h in the numerator? Okay, now we've got something to reduce with that h in the denominator, as long as h is not 0. I'm going to move that. Any questions about anything on that page before we move it? Kind of exciting, isn't it? So we have, after the h's are reduced, and everything that has an h in it, as h approaches 0, this product ought to approach 0. This product ought to approach 0, even faster, right? Because it's got h squared. If h is 0.00001, we've got to square it, which makes it even smaller, and then multiply it. So all these that have h to a power larger than 1 go to 0 even quicker. Now, is that what we thought we were going to get for the derivative of x to the fourth? Now, what seems likely then for our power rule or exponent rule, and then we'll validate this, that if we have the derivative of something x to the n, where n is a positive integer, okay, n times x to 1 degree less. Is that the pattern that you were thinking about? Right? As we looked at the derivative of x squared, x cubed, x to the fourth, seems to be that it's going to be that exponent times the same variable, whatever it is, x in this case, to 1 degree less. Now, to prove it, and I think this is worthy of being proved, some of the things today we'll just kind of look at, and they're almost too simple to even look at in proof form, but this one I think we ought to look at the proof. Is let's suppose that we have this function, x to the n, and we want to find its derivative. By definition. So x plus h to the n minus x to the n all over h as h approaches 0. So what we need is x plus h. I said we'd come back to this. Here we are. Now we're in need of x plus h to the n. All right, let's go with it. What's the first term? X to the n. Same pattern. Now we've got some letters and some numbers, but let's just use the same pattern. What should it be? Should be n times 1 divided by 1, right? Should be the coefficient of the next one. X to the 1 degree less, is that right? And h to the first. Not quite as simple looking when you've got, you know, h's and n's. It's easier with h's and 4 or h's and 7 or some number that we feel more comfortable with. Now it's going to get kind of ugly, but I think the pattern becomes clear. Now we're going to take n minus 1 times the number that's already here, which is n, divide it by 2, and that ought to be the next coefficient, right? Same pattern, everybody? I'm not trying to pull a fast one on you here. Same pattern. N times n minus 1 all over 2, x to 1 degree less than it was here. So it's n minus 1 here, so it's got to be n minus 2 here. H to the second. Now it's going to get good. This times this divided by 3. Is that right? For the next coefficient. Let me write that out. It's going to be n minus 2 times that, all of that, divided by 3. That's the next coefficient. Well, I'm dividing by 2, and then I'm dividing by 3, so I can divide by 2 and then divide by 3, and I'm just going to throw that in there. I can throw a 1 in there wherever I want to, can I? It's legal. And then I'm going to go back up here and put a 1 in there. I know it's 2, but that's the same thing as 1 times 2. Now you can probably predict the pattern of how this thing goes. It didn't look all that patterned until you look at it in terms of letters. This, by the way, the power of x is 1 degree less. So that's that term. So here's the first term of this expansion. Here's the second term. Here's the third term. Fourth term. What's the next term? Okay, Brandy, go ahead. n minus 1. There it is. There's the pattern. What's 1 times 2 times 3 times 4 called? 4 factorial. This is 3 factorial. This is 2 factorial. And 1, it can be 1 factorial. And if you want to back it up even further, the first one, by definition, is 0 factorial. 0 factorial is the number 1, by definition. So there's the next term of that expansion. So we can expand x plus h to the n. Now, one thing that is probably the most important thing is, after we get this pattern going, is that there's an h here, there's an h squared here, an h cubed, and an h to the fourth. So we've got higher and higher powers of h as we go, which becomes very important in the limiting process. All right, so we're going to come back to this. I'm going to get another sheet here. Sorry, I'm switching so much today. But that's what we needed x plus h to the n for, so we can evaluate this limit. So our function is x to the n. Our derivative was, and I've already written this, I'm just rewriting it. So now we have the ammunition to expand x plus h to the n. So I'm writing down now what we had written down on the previous sheet. Now eventually, we don't know what n is. N is a positive integer, but eventually if n is 10, we'll get 11 terms, right, in the expansion. Or if n is 100, we'll get 101 terms in the expansion. So eventually this thing will come down to, and its last term will be what? H to the n, right? So we don't know how many terms are in there because we don't know what n is. But it does have an end. From that, we're going to subtract x to the n. And all of that is going to be divided by h. Now let me go ahead and strike the terms that are going to be stricken. What drops out of the numerator? X to the n minus itself. We saw that same thing with x to the fourth minus x to the fourth, right? And then everything else remained. And in fact, everything else that remained, which mine is not correct here, I made a mistake. Did you see it? There's an h that should be here, right? The only term that doesn't have an h is x to the n. Here's an h, here's an h squared, h cubed, so obviously that was incorrect. Now it's been corrected. But one of the reasons I knew that was incorrect, shouldn't every term have an h in it, right, in the numerator? And that one term didn't, so something had to be wrong there. So if every term has an h in it, let's factor an h out. Now this is h to the n, and I just factored an h out, so it at least ought to have one less degree. And I don't want to divide all that by h. Let's multiply it by 1 over h. Now what is h times 1 over h? That's the nice thing about being able to factor an h out. They reduce. Okay, I'm back to that place now. Every other term, with the exception of this, has an h, right? And as h approaches 0, what happens to every term that still has an h in it? It approaches 0. So this has an h, so this whole term right here approaches 0. This has an h, that approaches 0. And in fact, every term that has an h, which in fact every term but the first term has an h, they all disappear as h approaches 0. And for our purposes, Cato, question first?
Yeah, on the third term, is that n times n minus 1, n minus 3, or should that be n minus 2?
N minus 2 should be.
Okay.
And that should be an n minus 3. And at this point, I don't know what it was originally, but it should be an n minus 2. But these all disappear because they have an h in them. And we're left with what? N x to the n minus 1. And isn't that what we wanted? Right? For the derivative of x to the n, we wanted the derivative to be exponent times same variable to 1 degree less. Now, so far, that works with what kind of numbers? Positive integers. It only works with positive integers. Wouldn't that be nice if it worked with other stuff besides positive integers? It'd be nice if it worked for x to the 1/2, or x to the negative 4th, or x to the negative 2/3. And in fact, it does. And we've seen that a little bit already. I'm going to change this. Any issues or questions or any more mistakes of mine that we want to bring to the front? Let me get it off there before somebody finds another one.
The second to the last h.
I didn't get it off quick enough, did I?
Is that h to, is that n minus 1? I couldn't see, it's kind of marked
This is
out.
h to the n minus 1 because it was to the n and we factored 1 out, so what's left is n minus 1, 1 degree less than what it was before we factored it out. All right, well, let me get it off there before somebody finds another mistake. We, I think, have done this problem. I think we have. So if we want the derivative of that, see if somebody has that. Trying to recall the ones that we've done that will be helpful to us right now. Pretty sure we've done this one. You know, now I'm thinking back, maybe we didn't do 1 over the square root of x. We maybe did this one. This will be just as helpful at this point. I think we did that one. 1 over x. The derivative of 1 over x, when we did this, using the definition of derivative, we may have in fact done this the first day we used the definition of derivative. We should have come up with this. Now, the rule that we have, that we are hoping is going to work for things other than positive integers, we're hoping that this same pattern, n times x to the n minus 1, it'd be really nice if it worked for other numbers other than positive integers. Well, 1 over x is the same thing as x to the negative first, right? And if this pattern were to work, what would the derivative of x to the negative first be? Exponent, which is negative 1, times x to the negative first minus 1, right? To the original power minus 1, which in this case is the negative second, and is that the answer that we got previously in this course? It is. So it appears that it's going to work for negative integers, right? That was a negative integer. This is not an integer. This is the square root of x, but we know that to be x to the 1/2. If you can check back, if you're not trusting of me, check back in your notes. I'm pretty sure we've done the square root of x because that's the first example where we had to use the conjugate of the numerator. And we got 1 over 2 square root of x. I'm positive we've done that example using the definition of derivative. Now, does that pattern then work should the derivative of x to the 1/2, if we use this nice, clean little shortcut, do we get that? Well, what should it be? 1/2 times x to the 1/2 minus 1, right? That's the pattern, the power rule or the exponent rule. And what is that simplified? X to the negative 1/2. And what is x to the negative 1/2? 1 over x to the 1/2. Same answer? Same answer. So it works not only with positive integers. We proved that. These aren't proofs, by the way. They're plausible arguments. Is it believable? Hopefully it is believable. But the first one we proved for positive integers, then we're thinking that it's pretty believable for negative integers as well, and rational exponents. So it works for all real numbers. So you'll see these two statements in your book. The first time through, if n is a positive integer, we proved this one. Kind of painstakingly proved it, but hopefully it was believable. And then the generalized version of that, if x is any real, if n is any real number, x to the n can be found, derivative of x to the n can be found the same way. as we proved it was found with a positive integer. Boy, that simplifies a whole heck of a lot. Not that that's a catch-all. That doesn't cover everything, but that's a huge time saver for finding derivatives of single variables, x or t or whatever it happens to be, to a power that is known. So if we have a function x to the 7th, we know that the first derivative or the instantaneous rate of change or the slope of the tangent line to the curve is automatically 7x to the 6th. Now, if you would like to continue to use the definition of derivative, other than having you psychologically examined, go ahead and feel free to do that on every problem that we do from this point. But as for me and my house, I will use the shortcut, okay, whenever possible. How about f of x is x to the negative third? Now, I'm kind of writing functions down somewhat gingerly still because there's still some rules that we don't have. We're going to get them. What should this be? Shortcut. Negative 3, x to the negative 4th. Is that right? Same pattern? And if you want to, write this as x to the 3rd for the original function, and you want to come back and write the derived function as negative 3 over x to the 4th, that's fine. They're equivalent whether you rewrite them in numerator-denominator form or not. And if the original function is x to the 2/3, the derived function is that right? So the exponent, the new exponent ought to be the original exponent, which was 2/3 minus 1, which is to the negative 1/3. Now, for evaluation purposes, we may want to know where that stuff is. Well, x to the negative 1/3 is in the denominator. And that's a cube root, right? So it's 2 over 3 cube root of x would be the derived function. Now, we haven't done that one. I think, did we do cube root? Yes, we did cube root in a homework problem where we had to use the alternative definition. Remember, we had to factor x minus a as the difference of 2 cubes. So we didn't do x to the 2/3, but we did do x to the 1/3. Questions on any of those three? Now notice I did not put a lead coefficient on any of those, as tempted as I was to write one down. It's just x to a power. So there's the next task, is to, what do we do when we've got a lead coefficient? Suppose we have 3x to the 7th. Okay? Basically, what we would like to do, we are in fact able to do. You bring that lead coefficient along for the ride. So it's, the derivative is going to be 3, so we just bring the lead coefficient along, times the derivative of x to the 7th, which is, we already found that to be 7 times x to the 6th. Now this may be one of the simpler proofs, and I don't plan to go through the complete proof, but if we were using the definition, and we say that we have this new function y equals some constant times the f of x, and we use the definition, wouldn't we be able to, and I'm not going to write it all out, but Wouldn't that c just kind of come along for the ride in both parts, right? C times the f of x plus h, c times the f of x, because we're going to put x plus h and x in there into the function. It has nothing to do with the lead coefficient. So couldn't we take that c and factor it out in front? It's in both pieces. And that's all we're doing. That's all we're saying that we're doing is we're just going to bring that lead coefficient along for the ride and take the derivative of the part that needs to be taken. So the derivative of the variable piece. So the derivative of a constant times a function is that same constant times the derivative of the function. So this c could be factored out, and in fact that by definition is f prime, right? So as your authors have written that out and called it the constant multiple rule, whatever you want to call it, it's fine, just so you know how to take the derivative of it. That's the important thing. If we have a constant times a function, the derivative of that is that same constant times the derivative of the function. So you'll hear me say many times, as I've said already a couple times, just bring that lead coefficient along for the ride. It's already there. There are the proofs of the next two are in your book. The derivative of a sum and the derivative of a difference. They are what we would like for them to be. We would like for the derivative of a sum to be the sum of the derivatives. It is. And that can be proved, and it is proved. That's probably even simpler than the proof I just wrote out, so I'm not going to write that out for you. Things that are added and or subtracted can be rearranged, right? As long as we take care of the addition and subtraction signs, and that's all they've done. So the derivative of a sum is the sum of the derivatives. That comes in very handy. And the derivative of a difference is the difference of the derivatives. But those proofs are in your book. I'll leave those to you to take a look at. So now what do we have the ability to take the derivative of? Let's say that our function looks like 3x to the 5th plus 4x to the negative 3rd plus 11x to the negative 1/5 plus 6. Could we take the derivative of that? Well, it's a sum, so we can. The nice thing about a sum is we can take the derivative of each piece and then add our result together. Derivative of a sum is the sum of the derivatives. And then we've got lead coefficients, right? So 3 times the derivative of x to the 5th is what? 5x to the 4th. Derivative of x to the 3rd. Excuse me, x to the negative 3rd. 11, derivative of x to the negative 1/5. Negative 1/5 x to negative 6/5, right? 1 degree less. And the derivative of 6, oh, I didn't leave any space for that one. Luckily, it doesn't need any space, right? The derivative of 6 is 0. It's a constant. Derivative of a constant is 0. Now, you probably should, when you have stuff like this, clean it up and multiply the obvious things. And there may be an occasion where you're asked to get rid of all negative exponents, so just put them where they belong, put them in the denominator. Okay, let's look at this example. Any questions on that one? Anybody? Isn't this pleasant to not have to do that definition of derivative every time? It's getting a little redundant there. JJ.
Even though the derivative of 6 is 1, why wouldn't it be plus 1?
Derivative of 6 is
Zero.
0.
Oh, okay.
Now, if you want, now that's an interesting point, because you might say, well, can we, since that's a constant times a function, in a way it is, right? That's 6 times 1. Can't we bring the 6 along for the ride and then take the derivative of the function? Well, you could. What's the derivative of the function? It's 0. So however you sidestep it or treat it, the end result is 0 in both cases. Anything else? Okay. Let me give you this function. Let's see, let's actually put the derivative to use here. I mean, it's nice to be able to find them, but if that's all we're going to do, that's pretty much of a waste of time. It's just finding derivatives. We want to find them for the purposes of being able to put them to work for us somehow. There's a whole lot of uses for derivative. So here's a kind of a low-level application problem, but it is an application problem. So let's start with this function. Now, if you can visualize what a cubic polynomial looks like, we know what they look like, those S curves, right? Some type of curve that changes direction twice is a typical cubic polynomial. Let's say we want to find the points at which the first derivative is 0. Actually, it's stated a little differently on my sheet of paper, but where I wrote it down, find the points on this function where the tangent line is horizontal. I probably should have written it that way. But don't those say the same thing? Where the tangent line is horizontal, the slope of the tangent is 0? So if we're finding where the tangent line is horizontal, the slope of the tangent is 0, and the slope of the tangent we know to be the first derivative. So let's find the derivative, the first derivative. With that nice new shortcut that we have, kind of clean and easy, what's the derivative of that given function? Okay, so we're going to write that one first. Negative 6x squared. Is everybody all right with that? And then the derivative of this is minus 12x, and the derivative of that is 0. Everybody okay with the derivative? See, I knew they'd be clamoring to get in here once we started getting the shortcut. See, they're just trying to get in here. Can't keep them away. Now, what do we want to do with this? So we found it. Once again, if that's all we're going to do is find it, it's not that worthy of all the effort. We want to know where the derivative is 0. Can I factor some stuff out? That leaves an x there and a what? Plus 2? Now redistribute that to see if it's the same thing, which it is. We set each one of these equal to 0. That's a nice thing about the product of things being 0. You can set each piece of the product equal to 0. So this is true when x itself is 0. So at those two x values, the derivative is 0. Now if I wanted to plot those points, 0 something and negative 2 something, to plot points, don't you go back to the original function, right? That's the relationship between x and y is the original function. So I would want the f of 0. What's the f of 0? This may not be quite as easy here. The f of negative 2, let's see, before 5 minus 24. No, and then we've got so we've got negative, what do we have so far?
13.
It's going to be 5 minus 24. When you cube it, you get negative 8, so it'd be plus 16. Is that right?
Yeah.
Negative 3? Is that right?
Yeah.
So tell me, and we'll finish with this, tell me what's happening on this curve, on this picture, where the slope of the tangent line is 0. What might well be happening?
The maximum and minimum.
Okay, possible high point and low point on the graph. So if we found 2 points on a cubic polynomial, do you think these would probably be the 2 most important points?
Yeah.
So this graph at 0, 5 and at negative 2, negative 3 is flat at that instant. The slope of the tangent is 0. And we'll do more with this, but a quick picture might be something like this, right? That's a typical cubic polynomial, and we found the 2 places where in all likelihood it changes direction. So those are probably the 2 most important points. Okay, not all of this is due tomorrow, but let me give you all the problems from this list, and we'll finish up this section tomorrow. Now remember that this looks like a whole heck of a lot of problems, but we now have the shortcut, so we're not bound to this long, tedious definition of derivative process. A couple of these problems have a definition in them. Problem 51 has a definition of a term in it, so I want to make sure you take a look at that, and then we'll address that. Problem 56 also has some terminology in it that we'll have to discuss. I will probably eventually collect this one, but it's not due tomorrow.
Is that 47 or
45, 47. Okay, that concludes lesson 25.